Good afternoon, everyone. My name is Tushar Gaikwad. I recently completed my master's in mechanical engineering at Western Michigan University. I'm going to present about vehicle velocity prediction using artificial neural networks and effect of real-world signals on prediction window. This is my presentation for SAE World Congress conference. My co-authors on this paper include Dr. Zach Asher, my advisor, Dr. Rick Meyer, Dr. Alvis Fong, and my colleague Farhang at Western Michigan University. Also include Dr. Thomas Bradley and Aaron Robinwitz from Colorado State University. Before we begin, I would like to give special thanks to Colorado State University and Dr. Thomas Bradley and his team for continuous support and guidance. I would also like to mention that this material is based upon work supported by the US Department of Energy's Office of Energy Efficiency and Renewable Energy. So these are the agenda for today's presentation. I will talk about introduction and background of overall project. Then we will discuss about the drive cycle development, LSTM model, assessment methods, and effect of different signals on prediction. At the end, we'll discuss about the summary, results, and future goals. Now, let's begin with the introduction. So, the shift we are witnessing towards the intelligent transportation system will be the most disruptive since the initial days of automobile. It has a potential to completely transform the movement of people and goods, enabling safer and smarter transportation. ITS consists of several technologies such as Advanced Driver Assistance System (ADAS), Automated Driving Functions (ADF), Vehicle to Vehicle and Vehicle to Infrastructure Communication. When we talk about the improvement of intelligent transportation systems, autonomous vehicle technology is key to improve driver and passenger safety. Over the recent years, the race towards the development of fully autonomous vehicles has accelerated tremendously. Many components make up an autonomous vehicle, and some of its most critical ones are the control strategies and AI software that powers it. With the increase in the computational capabilities, we are now able to train complex and deep neural networks that can learn crucial details and become the brain of the car, understanding the vehicle's environment and deciding the next decision to take. I would like to mention the motivation for the project, which is velocity prediction. The first motivation is for fail economy improvement. One of the strategy proposed for getting higher fuel economy is optimal energy management. In this strategy, vehicle velocity predictions determine the constraints of energy optimization problem to increase fuel economy. In my recent publication in SAE World Congress, I found that it shows significant improvement if we get accurate predictions. These red dashed line represents the input of vehicle operation prediction into the strategy. Another motivation is improvement of safety. So the strategy proposed for the safety improvement is known as collision risk estimator. In this strategy, vehicle velocity predictions can be integrated into collision risk estimator, thereby helping drivers to avoid accidents. Overall, in these both strategies, we can see that vehicle velocity is very prediction is very important in autonomous vehicle technology. These are the novel contributions for uh, for this research. We use different real-world signals in groups to estimate the effect on vehicle velocity prediction. We try to understand effect of different inputs in LSTM for varied prediction window. We use two assessment methods to understand results. Now we will talk about methodology. Here we discuss vehicle velocity prediction strategy. First, we gather the input data, which is collected from CAN, V2I, and radar. We give this input to neural network model, which is LSTM, which gives output of velocity prediction. We predict this velocity for 10, 15, 20, and 30 seconds. Then we assess these results with assessment methods and find the best possible velocity prediction. Now we'll talk about drive cycle development and signal recording. So our collaborators in CSU developed the drive cycle in August 2019 at Fort Collins, Colorado. They drove 2019 Chevy Blazer equipped with different sensors on a fixed route. The dataset from repeated drives were collected along the route by the same driver. This figure shows the actual map of the drive, which is urban area. These are the route details used for the drive cycle. So the vehicle consists of different sensors for gathering of the data. It consisted ADAS for detecting object in front of the vehicle. We were also able to get V2I information, V2I infrastructure data in the form of traffic signal information and segment travels times. We also collected ego vehicle parameters using Freematics logger. This map shows the signal along the drive route. The table besides that shows the various features we collected in the dataset. These are the plots for some of the recorded signals. The first plot consists of velocity on the map at different time steps. The second plot consists of the object detection by radar along the drive cycle. Here, in the first plot, the velocity on the map terrain is shown. In the second plot, the velocity for single drive instance with respect to time step is shown. Note that the time step we have used is zero point 0.1 seconds. Now we will talk about LSTM. LSTM is a special type of recurrent neural network capable of learning long-term dependencies from large datasets. It is also used to avoid issues such as gradient vanishing and exploding of conventional RNNs. A typical LSTM unit, often called memory cell, memory block, is composed of a cell, an input gate, an output gate, and a forget gate. The cell remembers values and the three gates regulates the flow of information into and out of the cell. The forget gate decides what information to discard from the cell. Input gate decides which values from the input to update the memory state. The output gate decides what to output based on input and the memory of the cell. Now, I want to talk about assessment methods. The results are assessed based on MAE. We also considered time shift, which uses cross correlation technique for better assessment. Mean absolute error is a measure of difference between the two variables. It is formulated over here. The time shift is a measure of time lag between the predicted time series and target time series. It is formulated below. So, we considered two hypothetical cases to understand these methods. So, here the blue line is the target velocity and the red line is the prediction. What is interesting in these two graphs is that MA for these two graphs is same. One plot shows upward shift and one shows sideways shift. Upward shift causes increase in MAE, but there is no increase in time shift. The sideways shift causes increase in MAE as well as in time shift. The effect of accuracy of MAE and time shift on fuel economy and safety improvement strategy is unknown. Important point to note that first case is not good compared to the second. In the first case, the prediction is wrong. In the second case, prediction is right but at the wrong time. Another thing to note that our prediction generally has both errors. For example, in this hypothetical case, the prediction has both the types of errors, MAE as well as in time shift. Now we'll talk about results. First, we divided the signals in seven different groups. Group A consists of current velocity and GPS. Group B consists of Group A and previous 5 seconds of velocity and ego and engine parameters. Group C consists of Group B and radar data. Group D consists of Group B and SPAT data. Group E consists of Group D and segment speed. Group F consists of Group E and radar. And Group G consists of Group B and segment speed. So we gave this input to the LSTM models and predicted and for different velocity predictions. And now these are the results. This is a box and whiskers plot for effect of signals on the prediction MAE. Here, x-axis represents groups of signals and y-axis is MAE. We obtained 10th second prediction for each group and for each drive instance. Line within the box represents median of the cross validation values. Cross within the box is mean of all values. We can observe that group with SPAT signals, that is group D, E, and F, have lower MAE compared to others, among which group T has the lowest MAE of 1.78 meter per second on an average. Similarly, this is box and whiskers plot for effects of signals on the time shift of prediction. We can observe that groups with SPAT data has lower time shift. These plot shows uh, the target versus prediction for group D and group E for one drive instance. Now we'll talk about effect of different signals on prediction window. The x-axis is groups of signals and y-axis is MAE in first and time shift in the second plot. So we can see that group D has the lowest MAE and time shift over here. We can also see that as the prediction horizon increases, the MAE and time shift both uh, increases. Data with spat data perform better in terms of time shift as compared to the others. This shows the plot for the forward prediction. So this is prediction for the next 10 seconds shown for every 10-second interval. This has been done to show the progress towards implementation side of this technology. Here we can see that the red line is prediction, which is very much following to the target line, and green line is shown as the previous velocity. So this is overall forward prediction looks like. This is also known as hairy plot. So if it shows more hairs, that means it has mispredictions. Now we'll talk about summary of the research. We talked about importance of automobile vehicle technology towards moving ITS. It uses AI to power different strategies to enable safer and smarter transportation. We also observed why vehicle velocity prediction is important part of implementing those strategies. We used vehicle velocity prediction strategy where group D used as a input to LSTM used LSTM as a model, and when we predict for 10-second prediction, and we assess the results based on MAE and time shift, we get the best possible solution, which is MAE of 1.78 meter per second and time shift of 2.35 seconds. In conclusion, for evaluating results, it is better to use MAE along with time shift. Also, dataset with spat data performs better in terms of getting accurate results. LSTM performs the best in terms of MA, which is 1.78 meter per second, at prediction window of 10 seconds. Increase in prediction window increases MA and time shift in case of ANN. In future work, we would like to study more drive cycle on different types of roads. We would also like to include V2V data and camera data, and also more V2I data. Then we would like to go towards implementation of trained model on NVIDIA Drive PX2 to test prediction strategy on the actual road. In the end, I would like to say the future belongs to autonomous vehicles, enabling safer and smarter transportation. I would encourage you all to please visit my WMU database for my thesis. Also, in case of you are more interested to know about further development in the project, please contact us at our email. Thank you. Thank you very much. Thank you.